So I want to thank everybody for being here to this Geo-Ruckus, Stirring Up Spatial Solutions, brought to you by GIS Colorado. And today we're here presenting Taylor Dorn's work. His session is titled Exploring Earth, GIS Planetary Geology, and Martian Mapping. So Taylor Dorn is a faculty member at Front Range Community College in Longmont, Colorado, where he plays a pivotal role in shaping the next generation of geospatial professionals. In his role, Taylor not only teaches a range of geospatial science courses, but also advises students on their capstone and practicum projects. He also leads the GeoX internship program. Taylor's teaching philosophy is rooted in the idea that education should be a balance of theory and practice. He's passionate about helping students not just learn geospatial science, but truly experience it. His dedication has made him a trusted mentor to many aspiring GIS professionals. Taylor's academic journey started at Texas State University, where he earned a bachelor's degree in physical geography, geology, and GIS. After Texas State, Taylor pursued a master's degree at the University of Louisiana at Lafayette, focusing on hydrology of intermittent rivers. Finally, he earned his PhD in geology from UCLA, where his research zeroed in on Martian landscapes, specifically geomorphology and alien processes. Taylor's work has extended beyond the classroom to some truly fascinating planetary GIS research. For instance, he has studied the wind patterns in Jezero crater on Mars, which is the landing site of NASA's Mars 2020 rover. His findings helped reveal how ancient and modern wind regimes shaped the crater's landscape, exposing the processes that eroded its famous delta. Additionally, Taylor has researched sediment transport in Arabia Terra, a region on Mars characterized by craters that act as both sediment traps and sources. His work shed light on how crater wall slopes influence the ability of sediment to escape these basins, contributing to our understanding of the Martian sedimentary cycle. These projects highlight Taylor's ability to bridge geospatial science with planetary exploration, using tools and methods that are not only impactful here on Earth, but also help us better understand other worlds. Behind Beyond his technical expertise, Taylor's approachable and engaging teaching style has inspired countless students, even myself, making complex topics relatable, and sparking curiosity in everyone he works with. So, without further ado, I'd like to present Taylor Dorn.
Excellent. Thank you, Ron. Appreciate it. It's quite the intro. Thank you. I have an intro slide too, but I'm not going to really spend much time on it because that was much better than the little bullet points that I had on my slide. So I'm going to,
I'll go ahead and stop sharing for you.
let me do this. Where is my, let's see. That, that at home, I have one screen. I'm not up at on campus. So cool. How's everybody doing? Like Ron mentioned, I'm Taylor. I want to say before, well, first of all, thanks for having me. Secondly, I'm going to go through quite a number of slides here. Given our time constraint and stuff, I'm not going to have that much time to go in depth. So there are kind of a couple of options that we can take. The first, I have my email and contact information stuff at the end of this. So if you do have any other questions that we just can't get to today, feel free sending me a message. I'm pretty on top of my email and all that kind of stuff. So if you want to talk about any of this stuff further or want any advising advice or anything like that, please let me know. The other thing, as I go along, and I say this to all of my classes, you do not have to raise your hand or anything like that. I am perfectly fine with you interrupting me. So I don't know. I don't know if you all can unmute yourself
I'm
or
I'm a classic interrupter.
no, that's perfectly fine. It is not going to throw me off or anything like that. If you have a question, just shout it out. You don't have to wait until I'm, finished my thought or anything like that. It is perfectly fine to interrupt me. Now, in terms of what we're doing today, I'm going to skip over this because Ron gave more than an intro about this than I could ever possibly do. Great hype, man. Thank you. I appreciate it. But yeah, those are all the places that I've been. The only thing that I do want to add before I get going here is um, all of the studies that I've been a part of, the papers that I've written, all that kind of stuff. You will notice, if you ever take a look at the CV or anything like that, or my website, that I never obtained a degree specifically in geospatial science. But every step along the way, whether it was hydrology or certainly planetary geology or planetary science, I use and continue to use GIS within everything that I do, whether it's, remote sensing data that I'm pulling, from NASA, or it's, using a drone that I'm flying myself. Okay. So yes. So what is our agenda for today? Like I said, it's kind of a lot. And what I wanted to focus on are three projects that I've worked on, at least that I've been in charge of myself for the most part, and how I use geology, or use geology certainly, but how I use remote sensing and GIS through all of these projects. And so essentially all of these projects involved some amount of field work, some amount of remote sensing or GIS data as well. Okay, so that's kind of the background here. At the very end, I do have a few planetary data links for you all. I'm not sure if this actual PowerPoint, I can send it if this will be ever posted anywhere. But if not, the links are pretty straightforward. And I can do a very short demo of kind of getting your feet wet with this stuff if time allows for you all. So most of my work, and I'm really focusing, the work that I'm focusing on here today is stuff that I did at UCLA. And when I was at UCLA, I got my PhD in geology, but really my specialty was planetary geology. Okay. And all of my projects that I worked on at UCLA were some combination of field work and remote sensing. In these, in doing this work, I primarily worked when I was on Earth in dry environments or arid environments, particularly the Mojave Desert. Obviously, I never stepped foot on Mars, but Mars very closely mimics what we observe in these arid environments that we have here on Earth. And what that means in the context of what we're talking about today is wind dominates. Wind is the dominant force that shapes the landscape. And so this is a project that I'm not necessarily talking about today. This is another thing that I was involved in. And this is actually a site in Nevada where we're looking at dust devils. This work is ongoing and still being published still and being presented at conferences. But you can see here, this is a whole bunch of dust flying around. You can see people in the background were wearing face masks, that kind of thing. This is not healthy to breathe in, certainly not at this volume, although, dust floats around us every day. We're still breathing it in, whether we like it or not. But certainly at this volume, this will do some damage to your lungs and your respiratory system. So we have masks. Wind is blowing around everywhere. It certainly shapes this playa that we're sitting on here in northern Nevada. And just to kind of get us up to speed, we're still kind of introductory thing. I know I'm taking a while to get into this, but this is probably a field that not many of you are familiar with, or at least some of the terms and stuff might be a little bit off-putting at first. But when we're talking about wind dominating landscapes, there are kind of two buckets that we fall into. The first are what we call depositional features. And again, most of this is just a matter of scale. So with depositional features, I think we've all been at the beach or maybe seen, we've looked under really clear river water or something like that and have seen ripples about this size. We're on the centimeter scale here. And then maybe we've certainly seen pictures of dunes, these large dunes that are on the tens, maybe hundreds of meters of meter scale, depending on where you are, what desert you're on Earth. But again, matter of scale here, depositional, the sand, whatever size our sediment is settling somewhere and causing these features to form. The kind of other bucket that we fall into are what we call erosional features. And we're going to take advantage of both of these buckets throughout the work that I'm sharing with you today. Erosional features, again, a matter of scale here, different sizes. But what we mean by erosional is whether it's sand, dust, whatever it may be, is quite literally acting as an abrader, kind of like a sandblaster on the surface of Earth or Mars or whatever, leaving behind these features. So this top one you can see is a benefact. We'll look at these a little bit later, but you get these nice little flutes. And by looking at the direction of these flutes, we can tell, within 180 degrees ambiguity in most cases, what direction the wind was blowing to cause these features to form. And the same goes for these yardings at the bottom. Okay. We can pinpoint a little bit better, but for the most part, you're getting 180 degrees. So this became really important to me. One, I love sand dunes. I love hiking around deserts, that kind of stuff. But also, this is an important issue because desertification, the drying of landscapes is increasing here on Earth, obviously with climate change. And so we're getting more and more regions on Earth that are becoming drier, that are becoming less inundated with water, have less water available to that landscape. So wind over time is doing more of the work in shaping our landscapes, especially here on Earth. And so, again, most of my work at UCLA was planetary in nature. So essentially what I was doing, Mars was my focus. I was looking at Mars, and I was looking at modern Mars specifically because modern Mars mimics arid, dry environments here on Earth. And I was seeing how that landscape can inform us about our current state here on Earth and certain landscapes that we have here on Earth, those being arid. So long preamble there. Thank you for sticking with me. We're going to move on to our first little paper here. And all of the work that I'm sharing with you is published. So if anybody needs access to any of these, I think most of them, I think all three of these are available for free. So there shouldn't be a paywall behind any of these. But all of these are published peer-reviewed work. So the first one is titled Intercrater Sediment Trapping and Transport in Arabia Terra Mars, Arabia Terra being a region on Mars. So the whole goal here was to determine essentially how craters act as both a source and a sink of wind-blown sediment on modern Mars. Okay, so basically what we're getting at here is what happens to sediment when it enters a crater. Does that crater allow that sediment to be transported elsewhere on Mars, or is it keeping it to itself? And what is the driver behind that? Okay, this becomes important when we look at the history of Mars. So way back in early Mars, when it was first formed, it was very Earth-like. There was water. We see now on the surface, we see deltas and rivers, ancient rivers, obviously do not have water in them anymore. And slowly over time, for a whole host of reasons that a little bit beyond the scope of today, became drier and drier. And now on modern Mars is the landscape that you see in this image below. Okay, the red planet, we see all pockets of sand. We see dunes across the surface. It's very dry. There's no visible water on the surface. Some ice, but no flowing water. Okay. As we, in this case, go from a landscape that is dominated by water to dominated by wind, as these conditions change, so do our process or the processes of accumulating and forming sedimentary rock. Okay, getting that accumulation and preservation of that rock. So old Mars, we got these nice little ripple features. We can go around Mars with a rover. We can zoom in, we can take these nice pictures, and we can tell which rocks were formed by water. So you're seeing these very fine laminated laminations, indicative of a rock being formed by water. And now on New Mars, we get a lot of these erosional features, okay? Not necessarily depositional. We see those vinifex, we see all of these other erosional features around the surface. So just the conditions are changing. I mentioned Arabia Terra at the beginning, a region of Mars. This is where Arabia Terra roughly is. It extends a little bit outside the bounds of the square that I have for you, but this is the main area of concentration that we wanted to focus here. And this is because for, again, a bunch of reasons, there are a lot of dunes within various craters in this region on Mars. And looking around this region, we saw a whole bunch of I saw a whole bunch of craters that were losing sediment volume over time. Some were actually accumulating sediment, but here's an example of sediment volume decreasing over time. So I have Mars year, our Earth year here, and we go from 2008 to 2010 to 2015. And inside these craters, I have a couple of arrows drawn. Okay, this white arrow, this black arrow, we can see these dark splotches in these craters. And in each one of these cases, over time, those black splotches decrease over time. We're losing sediment somewhere.
Disappearing.
Yes, disappearing. We don't know exactly where it's going. but it's leaving the crater for whatever reason. We'll take a look at that here in a second. So these sand dunes, because most of the sediment on Mars is basaltic, they appear in our imagery as these black splotches. So they're kind of easy to see in the landscape. And the imagery we get on Mars is excellent. At least in some cases, it's excellent. We'll talk about that here at the end of today for data sources, but we can get some really stunning high resolution imagery on Mars. It's not available everywhere, but in a lot of cases on Mars, we can get stuff where we can just keep zooming and zooming and zooming, and we can see these individual ripples on ancient lake beds or ancient riverbeds, that kind of thing. But here's what dunes look like on Mars. These dark splotches, we can see the crest of these dunes, really cool stuff. And from this, aside from what we're talking about today, we can see what direction they're blowing. We can make measurements over time. We can calculate volume estimates, all sorts of stuff. So that's one thing that we're going to take advantage of now. And we're also going to take advantage of something called wind streaks. And hopefully this shows up as clear for you as it does for me. But at the outset of some of these craters, we'll just take a look at where my cursor is right now. We can see kind of this dark streak coming out of our crater, okay? And again, these wind streaks are dark in some cases because sediment, primarily these basaltic dunes, are exiting the crater. And again, that gives us another indication of what direction the wind is blowing, what direction that sediment roughly is being transported in, okay? So we can use both of these, both sand dunes and wind streaks, to tell us something about the wind, the current wind regime, and where that sediment is being moved, okay? So the actual work here, a couple criteria that we set. One was we wanted to look at craters that were greater than 10 kilometers. And again, that was kind of the first filter to determine, we had to make sure that the crater was large enough. It was a large enough basin for things to actually accumulate. If you get to a certain size crater, then you run the risk of, well, sand is just kind of going around it, or maybe the sediment is hopping over it. So we needed a large basin to actually capture this stuff. And the second thing was something that we called a terminal dune field. Okay, so what a terminal dune field is in this case, or in all cases, a terminal dune field is where our dunes are dominantly towards one side of our crater, and we need them to be in close proximity to the crater wall. Okay, so you can think of these craters as giant cereal bowls. Okay, these are not just flat, but the crater walls, as we'll see, are to varying levels of steepness. So we wanted them to be close to the crater wall so that we could actually measure the steepness of our walls.
Close and steep?
Yes. Yep. After that initial criteria, we wanted to categorize them based on if they had or did not have a wind streak, and then the type of wind streak. So we're looking, and in planetary science, we use slightly different terms than geologists on Earth. We have to be a little less sure about ourselves. So you'll see these instead of dark or light or something like that, it's low albedo or high albedo. So that'll make sense to a lot of us in GIS, but it's a lot of the same terminology. So when we're looking at these dune field, again, we have our terminal dune field, one side of the crater close to the wall, and we have these dark streaks or these low albedo streaks, meaning that there's a source. That sediment is coming out of the crater. And at least the purposes of today, we had no wind streak. So again, here, terminal dune field, very close to the crater wall, dominantly towards one side. We can tell based on the shape, and if we zoom in, we can see even more the direction these dunes are going. But for whatever reason, no wind streak down here, meaning that this crater is a sink. It is just collecting sediment for some amount of time. It is not supplying sediment or sand elsewhere around Mars. So in this, again, this is all in one region on Mars. We identified 116 craters that had that criteria, the terminal dune field, larger than 10 kilometers, that kind of thing. 55 of those had wind streaks, 61 had no wind streaks. Went through, measured all of the directions of those wind streaks. And I have the breakdown for how many of those were the low albedo variety and how many were the high albedo variety. And this is kind of what we get, going through and measuring the actual slope of these craters to figure out if there's any correlation to those craters, okay? So a little histogram here where we're showing craters without wind streaks and craters with those dark wind streaks, so those low albedo wind streaks. Here if we break it down, we can see that these low albedo wind streaks, so the craters that are supplying sediment outside of the crater, I'm not going to say low slope, but fairly low slope, about 9.5 degrees. And then significantly different when we look at the craters, the crater walls slope that aren't supplying sediment outside, a little bit higher, 17 degrees. So the slope can play a pretty dominant role in shaping if sediment is able to go outside of the crater or if it's just a sink or a source. There was this intermediate variety that I'm not necessarily talking about right now because this is getting far into the weeds, but just so you know that there is not necessarily a strict cutoff, but we do have kind of this intermediate zone where kind of the two overlap a little bit. We also did go and measure a whole bunch of dunes on Earth that were climbing up various features and measuring those slopes as well. And so in all of these cases, we determine the cutoff of these craters to be about 15 degrees is the limit on how much, how steep you can get the crater wall for it to be a sink as opposed to a source of sediment, where that sediment is able to keep climbing up the crater wall and actually exit the crater. So what this all means, craters transition from being a source to a sink somewhere between 10 and 18 degrees. I know that's not like the definite thing, but in science, it's rarely a very specific number. So again, here it's more of a range, 10 to 18, but based on the measurements that we looked at and compared to similar environments on Earth, that cutoff is likely about 15 degrees. Doing this work, the sediment we determine, or the transport of sediment out of these craters, is primarily influenced by that crater slope. Obviously, if we are just filling up our crater basin with a ton of sand or a ton of sediment, there is a point where the new sand coming in can migrate over the old sand, and so you're effectively reducing the size, the volume of that crater. So other considerations can be made, but for the most part, our kind of first principle here is the actual slope of the crater wall is the dominant force in allowing or not allowing that sediment to exit. And then again, beyond the scope here, but we can also go back in the geologic history of Mars and actually look at the ages of these craters and tell us something about that regime. But anyways, that's what this last line is here. Our results suggesting that the craters formed since that transition from wet to dry tend to trap alien material and reduce the overall budget on Mars. And this has to do more so with the weathering and erosion of these crater basins. Again, a little bit beyond the scope here, but that's essentially what is happening. We don't have those same mechanisms for weathering and erosion on Mars currently than we did before. So our new craters tend to be much steeper and withhold sediment more than the older craters that are more degraded. Well, moving on to number 2. And this long title here, again published, is exploring the transition between water and wind dominated landscapes in Deep Springs, California. So this was an Earth-based project, a lot of field equipment that we did some comparative stuff on Mars that you'll see in a few slides. And really what we're looking at here is what are the surface changes that are occurring between an interface, in this case, between wet and dry. Okay, so I know I've talked a lot about Mars transitioning from wet to dry, and we have these playas on Earth that are basically mimicking that transition. The outskirts of the playa, certain times of the year, very dry, and then we have a wet interior. Again, that fluctuates depending on various levels of precipitation, but we can study this interface in wet and dry and determine and look at what type of characteristics that displays, what kind of morphologies we're getting, that kind of stuff, and hopefully tell us something about ancient Mars. We can do this basically on this principle, because we can look around Earth and we can look at various features. So if we look at a U-shaped valley, as geologists, we know that U-shaped valley was formed by a glacier. You know, we can look at deltas on Earth. We know it's being formed by water. And then of course, you know, now we all know that if we look at dunes, it's primarily formed by wind. So we can look at all these various features and we know basically what bucket of process it is that we're looking at. Okay, and at least in terms of Mars, you know, deltas, obviously no flowing water on Mars, but we have preserved deltas on Mars that we can look at. And so we just automatically know there was once water in this crater that formed this. It's basically a lake basin. Okay. I've showed this before. Again, we're still focused on this wet dry boundary. And we see this wet dry boundary all across Mars. So here is a pretty simple geologic map of a transitioning landscape on Mars. So this is several craters here. But if we do some stratigraphic mapping of this, we can see this transition of going from a paleo lake, so an ancient lake, and now what is currently being mapped, not surprisingly, is Aeolian dune strata. So there's dunes on the surface or in various portions of these craters here. So we directly see this transition on all across Mars. This image is taken from a rover. And again, here, just looking out, we see these thinly bedded mudstones all formed via water. And if we go a little bit higher, again, hard to tell, but if we zoom in and we look at some other samples and images that were taken from the same rover, these transition into some crossbeds indicative of being formed by wind. These are preserved dune strata. So two main ideas we want to get across, at least in this section. The first is that interpreting surface features just using aerial imagery can be very, very tricky. Okay. It's, sometimes we don't have a choice. We just have to rely on the morphology of certain features, but it can be misleading, as you'll see here in a bit. And second, that I tried to make the case that playas on Earth are understudied and underutilized, but they are an excellent analog that we can use here on Earth for studying Mars's transition from that wet to dry. So this is a video that I shot from a drone, and this is where we're at. So if anybody's been to California, you drive up 395. All along the left-hand side, you have the Sierra Nevadas. So you cross Sequoia. You're not crossing, but all on the left side is Kings Canyon, Sequoia National Park. A little bit further north is Yosemite. Then all on the right-hand side, this is all Death Valley. So very dry. This is where we see the dramatic change in a very green landscape to one that is very dry. Okay, the orographic effect is fully on display here. So all on this side is Death Valley. Where we're at in Deep Springs Playa. So I have this circle. This is the playa right here where my cursor is, just on the other side of these mountains. So the mountains you're looking at in this video, that is the very northern end of Death Valley National Park. So we're just right on the edge here. And then this is the playa. And again, hard to tell from drone footage because of how shallow the playa is, but a lot of this is dry. You can see patches where it looks like the sand or whatever this material is seems moister than other areas. And certainly in the playa, if we look in the background, maybe this is standing water. Who knows how deep that is? Kind of hard to make any guesses about that, but this is all fairly flat. Okay, there is not much slope to this at all, but it does change throughout the year. So what drove us to actually look at this? And it was actually just poking around Google Earth, believe it or not. And in poking around Google Earth, you can use that little slider at the top and you kind of keep going back. And here, if you go back to August 2013, these things show up, okay? And our lab was focused obviously on dunes. And so if we zoom in here, well, you know, these kind of have a dune-ish shape to them. What is going on here? So that kind of led us down this rabbit, okay? Zooming into other sections, you can see, I talk about this a lot more in the paper, but the connectivity of some of these are very isolated. And then you move to other portions of the playa, seem a little bit more connected, and that is disjointed, okay? And really going back, you kind of have to go back to these, but when we're looking at all of these dune morphologies, they can tell us a whole bunch of information, but one of the simplest dune morphologies to consider are Barkan dunes. And this is where we get our standard kind of nice crescent shape, this little half moon shape. This is kind of, if you tell somebody to draw a dune, this is likely the one they're going to draw. And these are really simple to interpret because we have these horns on either end. Those point in the downwind direction, so the direction these dunes are migrating. So it's really cool, very simple to look at. They're unidirectional, meaning the wind is coming from one direction, not multiple wind directions. And again, I think if we just very simply look at these features that we have on the surface compared to this textbook image that we have of Barkans, we can sort of see, we get these nice curvatures, obviously taken at different times. Are these things migrating across the surface and being preserved somehow? What is going on here? But I think everybody hopefully can see kind of the direction we were going with this and their similarity to Barchan dunes. So to answer this, whole bunch of stuff was actually placed out here. This is also a region where a lot of cattle graze at various times of the year. So we originally had equipment all around the playa and stuff was just wiped out over time and just wasn't reliable. So that is why we get this concentration over here to the west, southwest. Okay. But anyways, what we had going on here, we had a weather station that had a whole host of stuff for determining temperature and the pressure, how much rainfall was going on. There was a probe in the surface to measure surface temperature. So that's a big weather station. You can see that pictured here at B. We had a couple sediment traps because we were just building these, or I was building these myself, and built one, didn't like it. And then we ended up building a little bit more of a fancy one that is more reliable, that was used in other studies. And then we had trail cameras. So we had these trail cameras placed here. You'll notice all this stuff is basically downwind. So if we're interpreting those features from migrating from, at least in this screen, from right to left, all this stuff is downwind to hopefully capture any sediment, to capture any movement going across the surface, that kind of stuff. But we had these trail cameras that were at various heights that were just taking pictures every so often to actually see if any sediment was, we could see any sediment blowing, or if any features migrated across the image, that kind of thing. So this is all weather station data. So this is just looking at the wind speed. We're just doing some basic stuff here, seeing where the wind is blowing from, how fast is the wind blowing. But here, just by looking at the wind, the features that we were seeing on the surface, at least what we saw in 2013, that was the only image that we saw those features in. We're not in agreement with any of the wind directions that we were observing. We also didn't capture any sediment in any of the stuff that we built. And then also looking at this further, we saw that these features were primarily aligned with our shoreline. Okay, they're not being influenced by any particular, they have directionality to them, but it seems like more so they're actually just aligned with the shoreline, and that's it. There are dunes here. These are all vegetated dunes to the south. All of these features are to the north or to the northeast. And again, if we're interpreting these going from right to left or east to west, this doesn't make sense for it just doesn't align with any of the wind stuff that we measured. Again, keep in mind, all along the east over here is a mountain range. So all of our sediment supply is basically the opposite direction of where we would be interpreting these things below. So it doesn't make a whole lot of sense. But there are dunes down here. You can kind of make out some of the morphologies, but all of these are vegetated. These things aren't really going anywhere. They're all pretty stationary. And so comparing these with Mars and kind of getting at the trickiness of all of this, we did find a whole lot going on in this wet-dry interface. So again, we have these ancient preserved dunes around Mars. These are taken in Barth Crater. So again, we get these nice little crescent shapes that we observe in Deep Springs. This is an image down below that we took in Deep Springs showing roughly these crescent shapes that you can imagine at some point maybe being preserved, maybe not, but very similar if we were to make some of these measurements and getting the horn-to-horn width and the other length wise, going from the rear to where the horns extend to. Again, some other examples of other stuff that we saw in Deep Springs as well, particularly around where we had mud cracks. So we have polygonal fractures, or what we typically call mud cracks here on Earth. Again, the top image here is again in Barth Crater, where I showed that first initial geologic map where we show our geologic strata going from being formed via water to now wind dominated, but we get more polygonal fractures here. A little tough to see in this image, but there are other high resolution imagery where we can see more examples of these mud cracks around here. And then certainly in playas, Deep Springs, other playas here on Earth, lots of mud cracks because we get rapid wetting and rapid drying. So our soil's expanding and retracting. We also get evaporates around Deep Springs. So that's what's here on the bottom. So anywhere there was a depression, any minor depression, In Deep Springs, it would rain. And again, because of how arid the Mojave Desert is, that water would evaporate fairly quickly, and it would leave behind these evaporites in each of those depressions. And then similar, where on Mars, we can look around in various instruments, and then we again get some evaporites, these being jarosite crystals. So similar environments. So again, at least in this case, we showed, hopefully, that morphology alone is just insufficient to actually determine or interpret these features. In the paper, we go over a whole thing of how these were formed, but again, a little bit beyond the scope here. But morphology alone is not sufficient enough for us to make our interpretation. And again, hopefully made the case that playas are really good and useful analog for monitoring and studying further the transition that Mars underwent from wet to dry. So moving on to our last paper here is looking at the spatial variability of wind-blown abrasion and ibex dune field. Again, this one actually in Death Valley National Park. So this is one of the dunes that we're looking at. And really what we wanted to look at here is how abrasion varies with distance away from a sand source. So this has been done quite a bit. We've seen this done in wind tunnels. We've seen this done in the field, all looking at different abrasion rates of various materials, orienting those materials differently, north, south, east, west, that kind of thing, the angle at which those are oriented, and also putting those materials at different heights, okay? Nobody had yet to do it all together. You'll see what I mean by all together, is looking at the orientation in relation, the distance away from a dune field, putting these materials at different heights, all that kind of stuff, putting it all together. But we've seen this done in the field. We've also seen it done in wind tunnels. So a little bit later on, we'll talk about vinifacts, but basically what these are just wind-carved cobbles and boulders. Again, we have wind blowing over a landscape, in this case, Death Valley National Park. That wind picks up sediment to various sizes. And again, it's just sandblasting the landscape. So all around the field that we were looking at are a whole lot of examples of these vinifacts, where these rocks are just being sandblasted, and we can make some interpretation of the direction that the erosive winds were blowing. Obviously, throughout the day, if we go outside right now, the wind shifts a little bit. So these are capturing long-term erosive winds. A lot of factors go into this, but they're really interesting features, and they're quite useful, especially us looking at modern Mars. So Ibex Dune Field. So just as a reference, right here, you'll see the mountain range. This was Deep Springs. And if we go all the way to the southern side, park is pretty massive. We are now at the actual very southern entrance of Death Valley National Park. So everybody, for the most part, goes up, the actual roads. But if you have a 4x4, you can go this way and take some dirt roads before you get to pavement. You can go the fun way. So that's where we were, very southern entrance here, Death Valley National Park. And we chose this for a variety of reasons, because there are a number of dune fields in the park itself, but this one is out of the way. There's a lot of vinifacts here for us to study. Like I said, it's remote, so we don't have to worry about people messing with our equipment, taking anything, trampling anything, that kind of stuff. And it's also topographically confined. So we have mountains on nearly all sides. There's one opening here that is just funneling the wind, essentially, but it's pretty well confined, out of the way, out of sight. Not many people go to this area. So we again use the same weather stations that we used in Deep Springs. We had what I call the abrasion cubes, because I have a cooler name for these, but these are just all PVC, drilled a whole bunch of holes into them, and then put different materials. So on the left-hand side, we had basalt that was all picked up from the area. We had glass. We had these gypsum cubes just made from plaster from Home Depot. Just put them in ice cube trays, put a bolt in there, let them solidify, take them out, mount them. These are plastic. And then we had limestone, okay? And this same pattern was repeated on all four sides of the cube at very specific heights, okay? So lots of samples here to capture abrasion on all four cardinal directions. And then we had the sediment traps, the same one that we used, because this came just after we were doing the stuff in Deep Springs. So we used the same sediment traps as well that worked quite well. So lots of stuff there, gypsum samples. Gypsum samples were the best, and that's really what we relied on here. Again, the other stuff was more as a control, and you can see This actually got hot. So the stuff that we had basically melted in Death Valley. So some of the samples were missing, but the ones that stayed consistent and gave us good results were these plasters. You can see the gypsum plaster. You can see at these varying heights where you can start seeing the bolts and where you can't. And that gives you some indication of where the abrasion is actually occurring, at least at this angle, what's height it's occurring. Kind of cool. This is where all of the stuff was located here. So again, multiple weather stations, just as one as a backup. There wasn't much difference, obviously, between these. All of our abrasion cubes, our sediment traps, and then these 4 dashed lines are where we actually just walked across the valley and mapped vinifex at just random intervals. And we're walking, take 100 meters, take a sample of that area, walk 100 more meters, take more samples, that kind of thing, and map. So what we found, again, I have both stations here. At both stations, our winds were primarily northerly. And what this means northerly is the winds are coming from the north, not blowing towards the north. So all of our winds primarily coming from the north, but the stronger winds, the erosive winds, are primarily coming from the west and some in the east, but primarily from the west. And this is shown, again, kind of hard to see here, but the darker colors here with our scale are the higher velocity winds. So most of the wind comes from the north, but the erosive or more highly erosive ones coming from the west. And again, lots going on here, but basically I just wanted to pull this to show you that there is really no seasonality at all. The wind is pretty consistent throughout the year. Obviously diurnal changes, that kind of thing, but overall for the course of the year, not much change. This is one of the mini plots we made showing how much sediment was being collected at distances. So unsurprisingly, most of the sediment that was collected were the ones that were closer to the dune fields, and it decreases with distance away from the dunes, and it also decreases with heights. It's kind of makes like a little parabola, but basically we're concerned with the distance away from the dune field at this point. Most of the sediment we're collecting at heights at 15 and 24 centimeters, which is good because if we look at other studies that were done, this is the heights and the ranges where everybody else in the community is also collecting most of the sediment. So not a lot at the very bottom sample jars. It gets a little bit more at this 15 to 24 centimeter range, and then it decreases the further we go up in the wind column, unsurprisingly. And then abrasion. These plots get very complicated. So this is where you just stare at the paper for a little bit, but just to put it in simpler terms, we see the same trends that we were essentially seeing with this sediment collection, meaning that at each height, our abrasion was correlated very well with the amount of sediment that we were collecting at those same heights. And then the same thing goes with that relationship away from the dune field. So away from the dune field, not as much abrasion, closer to the dune field, more abrasion. And then the same thing with those heights where we're seeing that same amount of abrasion occurring between 15 and 23 centimeters. So all these data are lining up very nicely, which is what you want to see. And lastly, those west-facing samples. So when we're looking and envisioning those PVC cubes that I had, the samples that are on the west side of those PVC cubes all had experienced greater mass loss. And again, what we're looking at here is just those gypsum samples, because that was the more reliable data set that we had. Okay, but all of those gypsum samples experienced greater mass loss on the west side as opposed to the northeast and south. And then I also mentioned vinifex at the very beginning of this. So this is an example of some of those vinifex that we saw in the field. And this was cool because whenever we did our sampling of these, we measured 116 or mapped 116 of these things, and they correlated very closely with what we have with the modern wind regime. And again, these vinifex are records of long-term abrasive winds in a particular area, indicating that the wind regime here has not changed for a pretty significant period of time. And just some closing thoughts about this. So again, the actual magnitude of our abrasion decreases, fancy words here, exponentially with distance. So it's decreasing the further we get away from the dune field. We saw similar rates of that mass loss with they align very closely with what we measured with our sediment flux measurements. So both with the distance away from the dune field and with the height measurements and the directionality of all of this. And go into a little bit more detail with the paper, but all of our results correspond and correlate very nicely with previous work that was done individually in each one of these arenas. Okay, just looking at abrasion, just looking at sediment collection, that kind of stuff. So the last bit of here, I know I'm running out of time here, but I wanted to make a quick note on data sets because planetary data seems like quite literally out of this world. Like, where do I get all this stuff? Okay, so there are a few handy things that I wanted to throw here. The first is NASA's Planetary Data System, or what we call PDS. So I have the link here. This has everything. Everything that NASA does is hosted on this website. It does take a little bit, I will warn you, to get familiar with this. It's kind of the same as, when you're first starting out with Earth Explorer or the National Map or something like that. Takes a little bit, and even more so with NASA because of how much data there is, but everything is housed here. The only thing that you need to be concerned with is the lead time between these data being collected and them being released to the public. And typically that turnaround is 6 months, okay? All of these missions are funded with taxpayer dollars. There are researchers at various universities and colleges behind this. So whenever all this data first comes in, they have the first go at taking the data, analyzing the data, that kind of thing. That lead time is 6 months. After that 6 months, it gets released on the PDS and you can pull it. So if Mars is your thing, you can go pull up every single rover image that was taken on Mars Curiosity or something like that and pull it. Same goes with all of the lasers they're using to determine the mineralogy of everything. Anything you can think of, Mars, Venus, any other planetary body on this. It's really handy.
Asteroids?
Yes, asteroid stuff on here. There's Earth stuff on here. Literally anything you can think of is hosted on this website. The next thing is Google Earth. This is super handy. And I have a screenshot here. So whenever you first go onto Google Earth, it's going to show you Earth. But if you go up here and click, you get a few more options, and they might be adding more soon, but you can click on Mars. And when you click on Mars, it'll pull up Mars instead of Earth. And then down here at the lower left, there's this button called Layers. And you can, I didn't do it here, but there's this little drop-down box where it says Spacecraft Imagery. And when you click that, there are various buttons that you can click. You'll see a CTX, you'll see a HiRISE, you'll see some other stuff, and you can check those boxes. And when you do that, you can visualize Mars with that imagery, and you can zoom in and all that kind of stuff. But also, whenever you click on these images, it'll give you the ID and it'll give you a link. And when you click that link, it'll take you to a website where you can download that image, and that image can be brought into ArcPro, QGIS, whatever other software you are using. Really handy. And the last bit here is a GIS software called JMars. To use this, it's all free. This is all free. Everything I'm showing you is free. This requires a login. So you'll need to create an account if you don't have one already. And then there's this button up here called Download JMars. It is just a desktop icon. And again, this is just a planetary specific version of ArcPro, if you want to call it that. It doesn't have all of the same functionality or as much functionality as ArcPro, but this is a really handy way of doing planetary science that is also completely free. So within this program, you can search for specific imagery in a certain region. So you can zoom into an area, you can click one button, and it will show you all of the imagery data sets that are available for that particular location, be it a point or a polygon that you draw. Anything that overlaps that, it'll pop up. And from there, you can do a lot of mapping, a lot of interpretive stuff. You can download that imagery. You can move it to ArcPro. Anything you do in JMars, you can export and bring it directly into ArcPro, which I did plenty of times because there is some overlap between the two, but there is some stuff JMars does really well that you can then import. And vice versa. If you have shape files and whatever else in ArcPro, you can bring that over into JMars similarly. Okay. Now, I know that I have gone over my time limit. if anybody has any questions, love to hear them. If you want to get in contact with me about anything planetary related or any Front Range College questions, if you want to come take my course or any of our other courses, let me know. And just any career advice or anything like that. If you're looking to go into academia, talk to me. I'd love to talk to you. But there's my email. And then I also have a website called tdgeology.com, which has some other stuff on there as well, maybe some other links. And I think I have links to the stuff that I showed you in the past couple slides as well for downloads. But with that, I will, you've heard me talk enough, and I'd be happy to take any questions you have.
Thank you so much, Taylor. So there's some questions in the chat. I'll go ahead and read them.
Oh, nice.
So we got a comment, blowing, not scooping. Question, wind is entropy on Mars? Question, it would eventually normalize the landscape if there were no meteorites?
Yeah, so if you're not getting any new impacts, there's no new accommodation space being made. So then you would be at your limit as to where all the sediment can go. And so if we're going down, I'm just talking out loud here, and if you're going down that route, then we have now just created all of the sediment that we have on the surface. So I don't think everything would be covered up necessarily, but I guess given enough time, maybe. But I don't know. I don't know the actual calculation or rough estimate of how much volume of loose sediment we have on the surface and how much you could actually cover. But that is an excellent question. But I don't think so, because we have pretty deep.
Or how long it would take, yeah.
Yeah, and the length of time too. But that's a really interesting question.
Comment, Great Sand Dunes is a great location for a wet-dry interface,
Yes.
I think.
Yes.
Another question. So sampling using rover data on Mars would help ground truth satellites imagery?
Yes. Yep. That's what we're doing now. If you've seen the newest rover that's in Jezero Crater is leaving behind sample caches for a later mission to go and retrieve. So that is going to be the first actual hand samples that we have coming back from Mars. Everything we've done now has been, zapping the rocks with a laser to determine a mineralogy within a certain bounds, or looking at aerial imagery and doing remote sensing and making interpretations that way for the most part. There's some other stuff, but everything has been remote. And this will be the first go around we have of actually getting our hands on stuff. Not me. I will not advise this, but other people.
Very interesting. Comment, sorry about the cows. So no, there weren't no wind dunes. Oh, so no, these were not wind dunes.
No, correct. Yes, for that second project, looking at Deep Spring, they were not formed via wind. It seems like how we thought about it. And again, if you want the actual schematic, it's in the paper, but we thought of these as like bathtub rings because we have a certain amount of water in the playa. And as it recedes, it goes down and down and down. You kind of get the same thing looking at lake beds as that water decreases, but that's seemingly what these look like given this slope of these, and you can kind of get similar shapes if you start lowering the water. So the water lowers a little bit, sediment sits there, blah, 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 evaporates a little bit more and keeps going down is how we thought about it. And that's similar. There's other places on Earth where similar phenomena to a different scale, they're larger, but we compared it to other stuff that we're seeing in Botswana and Australia that seemed very similar.
Interesting. One more question. Your scale between Deep Springs and Mars on mud cracks, the two were vastly differing scales of images, yes?
Yes. Very different. Can be very different. They don't have to be that different, but yes, the mud cracks on Mars tend to be fairly large. A lot of factors go into this. The rapidness of wetting and drying and stuff. The mud cracks are a whole separate science, but yes, there are a lot of factors that go into how large of a polygon that you can get with those mud cracks.
Interesting. And then one more question. The scale of the Martian polygon fractures are very different than desiccation mud cracks. Could these be cryosphere features like frost haves?
Yeah. I'm trying to think of where I was at, but yeah, I could see going further north or further south on Mars and getting something that is that would be more influenced by ice. similar, but Barth crater, likely no, but again,
You'd have to have a
our
significant amount of water. Yeah.
yeah, our knowledge there is we're still limited, but I would doubt Barth craters under that much influence of ice.
One more question. So are
Mhm.
they hydrographic geomorphic features?
Wow.
In the playa.
Yeah, so in the playa, looking at those crescent shapes, those are more hydrographic. They're not aeolian in nature. We took core samples all around. There's no sand lenses or anything like that underneath the surface. It was all very clayey, it's very sticky, but there was no sand digging down. We dug down quite far. And truth be told, walking on the playa, you can only go a certain distance before you literally sink into the playa. And I think I got to about hip deep before I turned around. So there was no point where we could actually go to where those things were observed in aerial imagery on foot. All of it was via drone. But yeah, no sand, anything like that. They seem to all be hydrographic in nature, all formed by water coming up to a certain height and then evaporating back to some distance towards the mountains.
Very interesting. One more comment question. So don't sleep on the ground of the playa outside of a tent.
Yes. Yeah, for a variety of reasons. Yeah, I was camping out there one time and then woke up and poked my head out the tent, and it was probably hundreds of cows just right there. So yeah, it's fun times.
Then maybe 1/x times 2. Not sure what that meant. Um, if someone were inclined to do some citizen science with Martian data, is NASA PDS the main resource for GIS/remote sensing data?
Yeah, that's going to house absolutely everything. So yes, I forgot to mention this at the beginning. There is more data out there than we possibly have people on Earth to ever look at. Okay, so if citizen science is something that you want to do, or you want to make this a part of a school or class project or anything like that,
Sounds
do
like
it.
also an opportunity for artificial intelligence to help. Yeah.
Yeah. Yeah. People have tried to do, there's a lot of machine learning is like a big thing in planetary science now, that kind of stuff to just help do some of the like lower end kind of menial task type stuff. But yeah, there's a lot of data out there. So take it and do it. But PDS, this to answer your question, yes, PDS is a great resource that has everything. It is a little bit intimidating because of how large everything is there. If I were y'all, I would honestly just poke around Google Earth and switch it to Mars or whatever else they have now on there and poke around with those. And then JMars. I would get familiar with JMars because that again is a really easy place to get familiar with the imagery. So I know it says JMars, but it's the same as Google Earth where you can click around, you can change what type of imagery. And they keep updated, it's updated constantly.
Very nice. I'm going to definitely check that site out myself. One more question related to the previous question. Where can we find projection files for other planets?
Projection files for other planets. This is where it's not so great. There are common conventions across various planetary bodies. So I don't know about like Venus or if you're doing Titan stuff or whatever. Those are all going to be very specific. So the only, I don't know of any specific location, but um, this is going to take you poking around and figuring out what is common. I know in Arc Pro, for example, there are presets for certain like all of my Mars stuff. There are presets that just people use for Mars over and over. So there are planetary presets in Arc Pro to do all of this. Specific projection files, I don't know. I don't have a good answer for you.
Okay. And then Nathan says, yeah, what datum is used? What geographic reference system? Gradicool.
They're all different. They're all different datums. Every single planetary body has its own thing. So that is kind of the unfortunate thing. You got to get familiar, again, if Titan is your thing, if you want to do some icy moon stuff or something like that, get really involved with that community and look up what data sets they're actually using. And it's all going to be very niche, unfortunately. It is not once you get outside of Earth, everybody's using their own stuff. One thing. Every planetary body has its own community and own way of doing it.
Awesome. That was the last of the chats. Anyone else have any questions for Taylor? Okay, well, without that, we will slide over to Nathan Lowry, who is my co-chair. We're both co-chairs of the communications committee, so I'll let him go ahead and give out some friendly reminders of what's going on.
Some Yeah, that sounds great. Thank you to Dr. Dorn particularly and Ron for all this logistics and setup. If you are a member of GIS Colorado, thank you. If you are not, would you consider becoming a member? It is $50 per year. It is one of those gifts that gives and keeps on growing. And January is a wonderful time to remember. At least it's the best time for me to remember when to renew. So don't miss the opportunity to be able to do that. Those dues are used to help support the operations and logistics of the activities that we sponsor, which includes all the activities, Geo-Ruckus, the quarterly meetups, the training events that occur, and we'll talk briefly about what's scheduled coming up. But meeting in person and meeting virtually those in the field and learning from them is a principal way to be able to magnify and dramatically increase your knowledge, comprehension, and excitement in interest in geospatial science. So thanks. Our upcoming winter meetup is going to be at the Wellington Webb Building at the City and County of Denver. On West Colfax. If you don't know where that is, it is stone's throw away from the Capitol, and so it's an easy walking distance from there. And it's a wonderful, beautiful building used for lots of different civic events, but they've been very effective at the city and county in hosting events, including GIS Day this last November, and they're going to be hosting us and our activities that are going to be focused in part on government activities. A committee, a panel will be there. Training will be provided the day of February 20th. Frank Hoare is scheduled to provide his course on GIS project management. So we're very excited about that. And then, yeah, the National Geodetic Survey in particular and others related to surveying are going to speak specifically on the new release of the datum and state plane coordinate systems of 2022. So we're excited to hear more things coming from them at state and federal levels, and that's kind of the profile for the activity then. We're also going to be in April, the week of Earth Day and Arbor Day, the 23rd and 24th, I believe it is, in Southeast Colorado. So it'll be at the campus of Otero College. Look forward to seeing folks there. We had been there 13 years ago. It's great to frequent all portions of the state and to understand the Southeast in particular, the Arkansas Valley, the mesa and scarp terrain in that area. There's just a lot to learn and know about from folks down there, and I think it's going to be interesting both in the inside and outside participatory activities that we'll have then. Also, we want to thank our sponsors for today and for the year. Argus Solutions, Langen, Frontier Precisions, the Colorado Governor's Office of Information Technology, and Esri. And we are always looking for more sponsors, particularly to help with our meetups and some of the social activities, particularly lunch is often served by a sponsor. So if you're interested in doing corporate sponsorships of any of our meetups, that or offering coffee or maybe an evening meal, hang out in a dive for us to eat at. Those are wonderful opportunities to be able to make sure people know and understand what it is that you do and what your company or organization may provide in geographic information systems and geospatial science in general. Again, thanks for participating today. Dr. Dorn in particular, it's very exciting to learn about extraplanetary geography and geology in particular. And this was a treat for me, and I'm sure it has for many of us participating now and in the future when the video is available. We do make these available regularly on YouTube, and it may take us a little bit of time just to make sure we download and edit appropriately before it's released, but we'll let everyone know when those are available after the fact.
And thank you so much, everybody. Have a beautiful week.
Yeah, thank you, everybody. I appreciate it. Thanks for having me.
Thanks, Dr. Dorn.
Yeah, if anybody has any questions, feel free to get in contact.